So of course, what we've been doing really is a lot of algebra and polar coordinates. But since this is calculus class, what we really want to do is do calculus of equations in polar coordinates. The two examples that we're going to do really are arc length and area. Um, First, I'm gonna start with what I call the boring one. This is really not an interesting topic, arc length and um, and polar coordinates. So just bear with one example. I'm going to give you the formula and I'll show you how to use it, and then we'll go on to area, which is the much more interesting topic. So the formula for arc length, recall we use lowercase s for arc length, is this. It's s equals the integral from alpha to beta of the square root of f of theta squared plus f prime of theta squared d theta. So understand that since we're always writing equations in the form r equals f of theta, it sort of makes sense that we're going to integrate in the variable theta. That means that alpha and beta are going to be two angles, and then we're going to integrate in a function that gives the radius as a function of the angle. So let's suppose that what I want to do is find the length of this path, of this blue path, on the purple curve, which is r equals f of theta. I want to find the length of the path going between these two green dots. Well, we know that the variable is theta, which means that I'm going to need two values of theta, two angles. So what I've drawn in here is I've made a ray to show what it goes through the first green point to show what the first angle is, and I'm calling that theta equals alpha. I've made another ray that goes through the second green point, and that's going to be theta equals beta. By the way, just go back for a minute. Notice that a line through the origin with a slope, a line through the origin has the form theta equals alpha. In other words, theta equals some angle. These are sort of the equivalent of vertical lines when we integrate in the variable x. So we're integrating really from one angle up to another angle, the same way that in when we first started to do integration, we were integrating from one vertical line up to another vertical line. Okay, so the formula to do this is, we have to find the derivative of f, the derivative with respect to theta of f. We square it, we square the original function, we put them under the square root sign, and just apply the formula. So let me show how we would do this. Let's use the arc length formula to find the circumference of the circle r equals 2 cosine theta. Okay, so what is this circle? I've already talked about in the chart how this is a circle with the form r equals 2a cosine theta, has the radius a and the center a0. So this is really, this equation, this is the point A on the x-axis. So this equation defines this circle. So what I want to do is what I want to, sorry, this is not going to be A, because in this case I have 2 cosine theta, which means the A is just 1, so actually this is just going to be 1, and this is a circle of radius 1. That's what I meant to say. Okay, so this is a circle of radius 1, and we know that its circumference is just going to be 2 pi. But we know the formula for circumference, it's 2 pi r, the radius is 1, so we're going to get a circumference of 2 pi. The question is, can we do it using this formula? In other words, can we treat this as the arc length going from, let's say, this green dot all around the circle and back to itself, back to the same green dot? And we should be able to do that. And if the formula works, we should get the same number. That's understanding the length of the circumference as just being the arc length of a particular polar curve. Okay, so the thing to do is to understand what we have to integrate from, we have to integrate from something to something else. First of all, let's write out what f of theta is and get the derivatives that we need. So we're going to see f of theta is equal to 2 cosine theta. So putting this in the form r equals f of theta, this is playing the role of f of theta, like that. Okay. So if f of theta equals 2 cosine theta, then f prime of theta is equal to negative 2 sine theta. I'm going to need their squares, so the square of this, f of theta squared, is 4 cosine squared theta, and f prime of theta squared is 4 sine squared theta, because of course when I square the negative 2 I just get positive 4. So Okay, so what I need to do is I'm going to set up the integral. S equals the integral. I'll put in the limits of integration later. This is going to be the square root of 4 cosine squared theta plus 4 sine squared theta d theta. We can easily see, I'm just going to leave boxes here for the limits that we'll put in shortly. This is going to be the square root of 4 cosine squared theta plus sine squared theta d theta, which goes outside the square root. And we can see, of course, that this is just going to equal 1. So that gives us s equals the integral from box to box of, it's going to be 4 times 1. Square root of 4 times 1 just gives us 2 d theta. So the thing we need to know is where is integrate from what to what. Well, if this equation is r equals 2 cosine theta, let's think about what values are going to generate that green point, which is both the starting and ending point. We know that cosine of theta equals 0. We're looking for a radius of 0. And I've taught this enough to know that some of you are saying, what do you mean a radius of 0? The center is at 1, 0. This point here, this green dot, surely that's at a radius of 1. It's at a radius of 0 from this point. The whole apparatus of polar coordinates doesn't care that to the right of the y-axis is something that looks like a circle. The center of the universe in polar coordinates is the origin, and this point lies at a distance of 0 from the origin. So that's why I say that I'm looking for a radius of 0. I'm not interested in how far it is from this point. I'm interested in how far the green dot is from itself. In other words, from the point that's sitting right at the origin. So that's why it's 0. So that's going to happen. Cosine is going to give us 0 at pi over 2 and negative pi over 2. So if you think about it, what happens, in fact, I can sort of make a chart here where if I write theta and r, if I put negative pi over 2, r, which is going to be 2 times the cosine of negative pi over 2, or 2 times 0, that's going to give me 0. At pi over 2, r is also going to be 0. At theta equals 0, r is going to be 2. In other words, let me put in a blue dot here. In other words, at the theta equals 0, and again, starting at the origin and realizing that the x-axis is the line theta equals 0, the distance of the point that lies on this purple circle, where the blue dot is, the distance from that point to the origin that constitutes the center of the universe, right here, is 2. In other words, this distance is 2. That makes sense because if I plug in 0 into the cosine function, I get 1. I multiply it by 2, and I get 2. So this circle doesn't seem to be obeying the usual rules that a circle is going to be 2 pi unit is going to be an angle of 2 pi all the way around, and where every point on the circle has the same, has the same radius, the same distance from the center. That's because what I'm doing is imagine that I'm just a person sitting here at this origin, and I don't know what I'm looking at. I'm just looking at some shape off to the right. What I can see is that, first of all, this shape exists only between, well, I should draw them like this, only for angles that are on this side. In other words, between pi over 2 and negative pi over 2. There's nothing over in the territory here. I look to the left and I see nothing. There are no points on the circle that appear there. So the entire circle exists between negative pi over 2 and pi over 2. And its radius keeps changing because I'm not interested in the distance between the points on the circle and the circle's actual center. I'm interested in the points on the circle, how far they are from this center, the center of the universe. Okay, so all this to say that what we can see is that if we treat the green dot as our starting point, we generate that at negative pi over 2 and pi over 2. And all the points are generated by angles that are between those two numbers. So I can finally put in the correct limits of integration. That's going to be negative pi over 2 on the bottom and pi over 2 on the top. And yes, for the reasons I've just explained, this entire circle is formed by a range of angles that spans only 1 pi, not 2 pi. In other words, the total amount of distance between pi over 2 and negative pi over 2 is just pi, and that's just how it works. So for this circle. So, okay. So let's actually evaluate this integral. This is going to be 2 theta, the antiderivative of 2 with respect to theta is 2 theta from negative pi over 2 to pi over 2. And that gives us 2 pi over 2 minus negative pi over 2, which equals 2 pi. And that's, of course, exactly what we would have expected the circumference of a circle of radius 1 is. But we found it this way. So what's to understand in this problem? First of all, how to use the formula for arc length and polar coordinates. Second, I hope that you've gotten something out of this example in trying to understand why what the difference is between the center of the figure we're drawing and this kind of center of the universe is what I'm pointing to with the purple arrow, and how when we're trying to figure out where the object is and what angles we actually have to consider, what we're doing is figuring out where it is within what angles from the center of the universe, not the center of the object. So that hopefully, if you go through this, you'll understand why this entire circle is formed by angles from negative pi over 2 to pi over 2 instead of the usual 0 to 2 pi for a circle that was actually centered at the center of at the real center at the origin, the center of the universe.